seats at the front. So if you do find that you're in need of overspill, the front row is still available. And you're very squeezed, I know, as well for time. So I'm just going to be really brief. I'm David Wallace. I'm the director of the Newton Institute. Sorry I wasn't here when you launched. Normally programs start at 5 to 10 or 10, and I had that in my head, so I missed your 9 o'clock, 9:15 start. Really pleased, just very few things. Firstly, welcome to you all. I hope that you have a really stimulating and interesting time here. The Institute is simply dedicated to ensuring that you make the best of your available time here. If you have any queries or whatever, then please don't hesitate to ask at the desk. We're a bit stretched because of the total numbers, and we're short with people on leave, but everyone will do the very, very best that they can to make sure that this is a productive and enjoyable conference for you. I guess the other things I should say, please, is to if you could switch off your mobile phones, because even when they're on silent, we pick up in the recording system the that you'll be aware of. So if you've got any mobile devices on laptops or on phones, could you switch them off, please? Apart from that, I think I should just say really thank you very, very much to Nick, Sarah, to all the organizers for a really interesting program. The Institute's moved on a bit from being sort of pure maths and a bit of theoretical physics to having a much broader remit. And undoubtedly, this kind of program in the bio and medical sciences underpinned by maths is going to be an increasingly important part of what the Institute does in the future. It's great to have you here. At this point, I will scoot and let you get on with it. Excuse me, over to Mark.
Thank you. So without more ado, we're going to hear from Jeff Saucerman about ß1-adrenergic receptors.
So I'd like to first thank the organizers for the opportunity to present. This is looking to be a really exciting conference to be at. So the beta-adrenergic signaling pathway is one of the core receptor signaling pathways that modulates heart contractility and heart rate. This pathway also plays a very important role in a variety of heart diseases, and one of the ways in which we can see that is that beta blockers, which are drugs that act on the beta-adrenergic receptor, are one of the most highly prescribed classes of medicines. This is widely prescribed for things like high blood pressure, heart failure, arrhythmia, and coronary heart disease. Yet surprisingly, the actual role and mechanisms of this pathway are still not well understood in the context of heart failure. And even further, it's not truly known how beta blockers are working physiologically to be effective. Over the past several years, we've been developing biochemically and mechanistically detailed computational models of this pathway, focusing on the beta-1-adrenergic receptor signaling pathway, which is the most highly expressed receptor in the cell, and focusing on this cyclic AMP and PK-mediated pathway, looking at regulation of contractility and relaxation. This pathway also acts significantly through the beta-2-adrenergic receptor and modulates overall a number of different phenotypes that we are now at various stages of computational models for these other phenotypes as well. So now that we've started developing these computational models and focusing on some of the basic biology of these pathways and the importance of various biochemical interactions here, we're now interested in using these models to examine the mechanisms of drug actions. In particular, here we're starting to look at some of these basic mechanisms by which beta blockers might work. And so our approach is to integrate the systems models that we've been developing with some key experiments to help address these questions. Here I'll be showing just a first stab at 3 sub-questions in this area. One of them, which is really just a restatement of how do beta blockers work, is highly controversial whether beta blockers work sort of in the trivial way by shutting down the pathway, or others have described that beta blockers may work in a way that's said to be paradoxical, and that blocking the receptor may actually enhance receptor sensitivity. And so we're interested in taking a look at that in our models. Further, however beta blockers may be working, perhaps by enhancement of receptor sensitivity, we might be interested if different clinically used beta blockers have different efficacies or might work through different mechanisms. This would provide an opportunity for more optimized therapies or using particular beta blockers in certain situations versus others. Finally, there are a number of rather prolific beta-adrenergic receptor polymorphisms that could potentially affect how well certain beta blockers work. And this could open up an area of personalized medicine. So this is a schematic of the model that we've previously described. And here what we need to do is update some of the details about this beta-adrenergic receptor to account for some key things that were missing originally. We did this using what's called an extended ternary complex model, which models the interactions between the receptor, ligand, and G proteins. What was missing before is it's actually been described originally by Bob Lefkowitz in '93 that receptors spontaneously switch between an inactive state and an active state independently. And it looks like what these various ligands do is actually binding selectively and stabilizing inactive versus active states, and that had not previously been described. And that becomes really important here because the various different beta blockers bind more or less selectively to inactive versus active states, and also some of the polymorphisms that have been described affect the balance between these states. And so then we formulate this model using mass action kinetics that in this case we reduce to algebraic relationships using a rapid equilibrium assumption because the kinetics of these individual reactions are much faster than a lot of the dynamics and other steps of this cascade. So now here are just two quick examples of simple validations of the model. These are in fact receptor binding assays, so not looking at signaling function, just binding of different ligands in the presence, under normal conditions without GTP, and then also with GTP, so this is the G protein here, saturating with GTP kicks off the G protein, and so you see what the receptor does in two different conditions. We can also look a bit further down the pathway to the functional effects from receptor down to cyclic AMP and look at how much cyclic AMP is produced for a range of different ligand concentrations. Here I'd focus on the EC50 point of half maximal activity, and also that the model is doing a pretty decent job of simulating the basal activity of this pathway, which is substantially higher than what it had been in previous versions of our model. And then now connecting some of the signaling pathways to the cellular phenotypes that they regulate. This is an example of the data that we're now generating with simultaneous calcium and cell shortening assays. And so now we can predict how changes in isopaternal, the ligand for this receptor, stimulate a dynamic response in cyclic AMP, and how that dynamically enhances the calcium transients of the cell. And that this matches up, fairly reasonably with the calcium transients that were recorded, and these are example sarcomere lengths that I'm not showing here, but we're now also included in these models. Okay, so now that I've set up a framework where we've got an appropriate model for addressing these sort of questions, let's jump right in. So what we're doing here is we are simulating what might be a chronic high catecholamine level that is often seen in heart failure. And what happens in this condition is that cyclic AMP will be high, the receptors will desensitize, and the calcium system is going to be pushed to a fairly activated state all the time. And the system is just sort of stuck in this mode because it's got high circulating catecholamines. And what happens is that then if there's a subsequent acute stimulation, like you might see in exercise with high local ligand concentrations, the system is no longer to respond as it once did, as desensitized. And we can quantify the sensitivity as the change in cyclic AMP or calcium concentration due to this secondary acute stimulus. And so now when we simulate what's going on with beta blockers, we see that if you've got a beta blocker on board here, that the system no longer responds to this chronic stimulation, which is good. So this is sort of like the trivial explanation of beta blocker function, that is shutting down the pathway. But really interestingly, if you have a second, more acute dose of isopaternal or a ligand, the system is still able to overcome that beta blocker and have quite a large response to that stimulus. And so in this way, the pathway is not sensitive to these chronic stimuli, but has enhanced sensitivity to acute stimuli. And down here, I forgot to mention it, it shows the example calcium transients corresponding with those conditions in the model. So these results, these early simulations would suggest that yes, in fact, beta blockers can both do the blocking of chronic responses, but also sort of paradoxically enhance sensitivity to other stimuli. So now, if these sort of behaviors are possible, we'd want to know, well, do the different clinically observed phenotype beta blockers act differently? And so we found this really nice data set by Hoffman et al. And what they did is they expressed these beta-adrenergic receptors in human cell lines, and then did biochemical assays looking at cyclic AMP and receptor binding for this entire panel that includes both beta-adrenergic agonists and antagonists. And so then what we did is then we fit the model just to the ligand-specific parameters, which are this binding affinity here and this alpha, which talks about the selectivity of binding to the inactive or active state. And one of the things that was really interesting that we saw here is that for the beta agonists, in all of those cases, you had very low sensitivity because you get this desensitization of the network. And overall, the beta blockers enhance sensitivity, which is consistent with what I just showed you. But the enhancement of sensitivity was surprisingly variable across these different beta blockers, which might suggest that they work either very differently in terms of efficacy or by different mechanisms. The next question would be, well, what about these different beta blockers made them effective or ineffective? And if you look at these two parameters that we fit, the KL and the alpha, what's interesting is that there wasn't a single parameter that explained their efficacy. What actually seemed to work best is that if you had a high selectivity for the inactive state and you had a tight binding efficiency. So one final question I'd like to look at here is whether some of the beta-adrenergic polymorphisms might affect how well these beta blockers work. Somewhere around like 70 to 75% of these receptors are actually this glycine 389 arginine variant rather than the classical glycine variant. And we were able to use, again, data from human cell lines to identify how some of the model parameters might be different in that case, and then simulate how the myocyte response at the signaling levels and contractile levels might be different with beta blockers for these two receptor polymorphisms. And what we found is that this arginine 389 is sort of constitutively active even under the case of beta blockers, and that for this polymorphism there might be a significant benefit at further improved beta blockers that pulled down this constitutive activity. So to summarize, we, through these early simulations, are finding that yes, beta blockers may in fact do this paradoxic enhancement of receptor sensitivity, that beta blockers can significantly differ in their enhancement of the sensitivity, and the model is helping us find guidelines for which blockers might be more effective than others. And finally, that some of the common polymorphisms that are out there may significantly affect which drugs might be working in which situations. So with that, I'd like to thank the people that did this work. Ryan Connolly and Sean Meredith did most of the modeling, and Robert Amanfu is a graduate student who's been doing the experiments. Thank you.
Thanks, Jeff. So any questions? Shall I kick off? So you talked about desensitization. I suppose that's really very important for your work. So how did you model that? Because I know that it involves internalization of the receptor and so on.
Right. So there are two mechanisms for receptor desensitization in the model right now. If I just there are two mechanisms for receptor desensitization. Actually, this diagram only shows one of them, which is that the beta-adrenergic receptor stimulates GERK2 to phosphorylate the receptor and desensitize it. And then also the other mechanism is protein kinase A phosphorylates the receptor and desensitizes it. Both of those mechanisms are in the model. For the beta-1-adrenergic receptor, it's a similar balance between these two feedback pathways. But this desensitization process is really important, and one of, particularly Wally Koch is looking at ways to therapeutically target that as an alternative to beta blockers.
Salama.
Did you look at the differences between chronic agonist delivery versus the kind of transient delivery by the nerves? Because in large part, this chronic effect is probably mediated by adrenergic glands versus the very local and highly heterogeneous neural effects.
Right, and so that's what we're sort of trying to mimic in terms of our chronic lower dose response versus in which we saw that the beta blockers would be able to totally suppress that versus a higher, more acute response that would be more like an exercise response or nerve stimulation. What we haven't done is gone back and looked at what happens with more of a transient stimulation. Right now we're just kind of doing step inputs so that are more closely like the experiments that we're working on right now. But that'll be really interesting to see whether the dynamics of the input significantly affect this response.